Hi, my name is Ben Bienema, and you're watching a demonstration of my latest PIC microprocessor project. The goal of this project is to create a two-channel sensor that reads and stores data to a memory module and then outputs to a PC for data processing. We'll start off first by going over the hardware. For our microprocessor, we're using a PIC 18F2550. This is connected to our circuit using a USB bitwhacker kit provided by sparkfun.com. All this does is contain our basic application setup, so we don't have to do this over and over. It's got a reset button, a couple LEDs to blink, and a power source, which actually, because this is such a low power circuit, we're able to power our entire project through a USB port of a computer. Right below that is another module from sparkfun.com. It's a serial communicator. Just allows us to do easy communication between our PIC and our PC. Now we have an EEPROM memory module, which will store both channels of data from our A to D conversion. And we have our thermistor, which does our temperature reading, and we have two leads connected to our signal generator, which just gives us a nice and steady 1.5 Hertz sine wave. Okay, this is our PC interface. We're just using a real simple serial communicator here. We chose not to spend a lot of time creating a user interface for this, but it's a reliable one nonetheless. We'll go ahead and give our PIC a reset, and you can see it displays a command prompt here. It basically tells us that anytime we can enter 0 to begin sampling or enter 1 to read out from memory. Since we haven't set anything to memory yet, it's probably not going to give us anything good. And then at any time we can enter 3 to set our sampling rate, or enter 4 to specify our number of samples. So let's go ahead and we'll just fire the defaults, which it states is at 100 Hertz and 100 samples. Okay, so it tells us it's sensing, and then you see it goes into this digital voltmeter mode. If we had a nice, if we were able to clear the screen on this communicator, we wouldn't have to have this long list of readouts, but nonetheless it gives an accurate reading from our voltmeter, or from our temperature sensor. Let's go ahead and put my finger on the temperature sensor. You can see it goes down, maybe you can see that, and then goes back up. Okay. Go ahead and enter to stop it, and then 1 to read out, and it gives us our data. So that's good. Looks like we are well connected to our sine wave, just reading these numbers here, just checking that. I'm going to go ahead and clear the screen now. Let's go ahead and try to set our sample rate here. So we enter 3 to get into sample rate mode, and tells us we can specify an entry between 10 and 250 Hertz. We'll just check to make sure that our error checking is working properly. Enter 300 Hertz. It gives us an error. Okay. Go ahead and enter 200 Hertz then. Okay, so the sample rate is set at 200 Hertz. And we'll go into mode 4, which is our number of samples. So any integer between 10 and 9,999. And we'll just set this at 500. 500 samples at 200 Hertz shouldn't take too long for us. Okay, so we're all set here. And we'll go ahead and hit 0 and start sensing. So it's sensing right now. And there it goes into voltmeter mode, which means it's finished sensing. I'll go ahead and hit enter to stop sensing. And then I'm going to clear the screen. This is just going to give us a nice clean data readout. So I'll hit 1, read out our data. It's going to take a little bit. Just doing 500 points here. Once this data rate is complete, I'm going to save it to data.txt, which our MatLab file will be able to read out and create a nice plot for us. So I'm just going to, tells us it end transmission, so we know it's done reading out. I'm just going to erase this because MATLAB's not going to like it. Save. Sorry, set save as data.txt. Save it here. Okay. We'll open up our MATLAB editor. This is a very simple program I wrote just to quickly give us a temperature readout and our signal generator readout. Go ahead and run this. There we go. Open up this program. So this top line here is our temperature sensor. We didn't hit our temperature sensor while I was running, so it's a nice straight bar. I'll make sure for our next readout we do that. And then here we can see our sine wave, not very smooth, no bumps in it. Zoom in at 200 Hertz, we should get a very smooth sine wave. If we zoom in, we can see it's very smooth. If we go down here to our temperature sensor, we can see that it's a little more jittery. It's a very cheap thermistor. So it's not going to give us as accurate as sensing. But as you can see, we're staying pretty close between 27 and 27.1 degrees Celsius. So this error is, if it were for an outdoor thermometer or something like that, very acceptable. Yep. So that is our data readout. Let's go ahead. Let's get a. Let's actually use our thermistor and make sure we do that. So I'm going to enter 0 to sample again. So we're sensing. I'm touching the thermistor. Okay. So you can see the thermistor's working perfectly. Okay. Enter. Let's get a nice readout here. Wait for it. Go ahead and close this figure. And delete our end transmission. Save it. And run our MatLab code. It's as easy as that. Okay, so you can see we had a little bit of fluctuation here. It's hard to read in this upper plot, which is why I created the second one. You can see it as I touched it. It rose to just above 28 degrees Celsius. I guess I'm not too hot today. Okay, so right now we've got our circuit connected to an oscilloscope. The first thing we see here is our oscillating bar. This is our sine wave output at 1.5 or 6 Hertz right now. It's fluctuating a little bit. So that's just our sanity check, make sure our oscilloscope is working well. Right now I've got it set to run at 150 Hertz, which should give us a 6.6 second or millisecond interval between read processes. So we should see 6 and 2/3 bars between each high point. Okay. So we see we've got 1, 2, 3, 4, 5, 6, and about 2/3 between our two high points on our second channel, which is straight from our clocked interrupt or timer interrupt. We're going to go ahead now. We'll set that to 200. And this is just kind of prove that we are actually changing our sample rate. It's not all mind games. So now we should have 5 bars. We've got 1, 2, 3, 4. We're just a little bit under according to this oscilloscope. Fire that again. Alright, we got a little bit of margin of error in here, so we're not quite lined up. So we're pretty dead on with our 200. We'll go ahead and go now to 250. Just to prove it again. Alright, so at 250, let's fire her up. Okay, so we're right on here. We should have 4 milliseconds, or 1, 2, oh, lost it. 1, 2, 3, 4 milliseconds between interrupts. So 250 Hertz corresponding directly to 4 milliseconds, we're dead on. Again, I'm Ben Bienema. This has been my latest PIC project, and thanks for watching.